Welcome, dear students. In the last class, we have already studied the transistor biasing, that is, applying a DC voltage to the transistor circuit so that it works properly, is called transistor biasing. Why the transistor is biased? The main function of a transistor is to amplify or gain the small signal. Gain means amplify or increase the small signal. If you apply a small signal, that is small voltage at the input, you get a large voltage at the output, and this is called gain. How do you define gain? For example, if input voltage is 1 and if you get output voltage 10, how much it is gained? 10 times. Similarly, if the input voltage is 2 and if the output voltage is 50, how much it is gained? 25 times. 2 into 25 is 50. Therefore, gain is defined as simply output by input. And there are two types of gain, forward gain and reverse gain. Forward gain is always more than the reverse gain because forward gain is defined as the ratio of output to the input of a transistor. Similarly, the reverse gain is defined as the ratio of input to the output of a transistor. Usually, the gain is denoted by the letter A. A suffix I stands for current gain, and A suffix V stands for voltage gain. P stands for power gain. Therefore, a gain can be anything: current gain, voltage gain, or power gain. All the gains are the ratios of output divided by input. Example, voltage gain, output voltage by input voltage. Power gain, output power by input power. Current gain, output current by input current. Since the ratio have no unit because both numerator and denominator are the same quantities, voltage by voltage, power by power, current by current, they have no unit. It is only a magnitude. Therefore, gain has no unit. Gain has only the magnitude. That is how much the input is amplified or increased at the output is referred as gain. You know that the transistor is a three terminal device, but actually you need two terminals for input and two terminals for output. Therefore, for that we make any one terminal of a transistor. Among three terminals, emitter, base, and collector, one terminal is made common for both input and output. If the base is made common for both input and output, it is called common base configuration. If the emitter is made common for both input and output, it is called common emitter. Similarly, if the collector is made common for both input and output, it is called common collector. That there are three configurations: common emitter, common base, and common collector. So now the gain of a given transistor is usually obtained by the doping concentration. There are two types of transistor, NPN and PNP. However, there are three portions: emitter, base, and collector. How much the emitter, base, and collector are doped, depending upon the concentrations of doping, the gain is decided. And for a given transistor, the gain is already calculated and it is mentioned in the data sheet of a transistor. Therefore, the gain of a given transistor depends on which type of configuration it is connected. Example, when emitter is made common, you call it as common emitter configuration. And the gain, current gain in common emitter configuration, CE configuration, is denoted by beta. Then by the definition, gain is the ratio of output to the input. How the common emitter configuration is there? See, this is the common emitter configuration, where the emitter is made common for both input and output. This is our input and this is our output. Now, this is the base and this is the collector. Let IB is the base current, so that the IC is the collector current. The current gain in common emitter configuration is denoted by beta. The gain is defined as ratio of output by input. Therefore, current gain beta in common emitter configuration is defined as ratio of output current to the input current. That is IC by IB. Therefore, beta is IC by IB. So, from this equation, you can calculate the collector current, which is given by beta into IB, where beta is the current gain of a transistor in C configuration. Similarly, if you consider a transistor in CC configuration, or you consider a transistor in CB configuration, in CB configurations, I will write these CB configurations. Here, the base is made common for both input and output. Here, the base current, and the arrow mark shows that it is an emitter, and this is base and this is collector. Therefore, here emitter base is input, collector base is output. Since IE, the base current flows in this direction, the collector current flows in these directions. Now, this is the emitter current IE, and this is the output current IC. So, in common base, IC is the output current, IE is the input current. By definition, gain is defined as ratio of output by input current, IC by IE. The same current gain, but in the common base mode, is represented by alpha. The gain in common emitter mode is represented by beta. The gain in common base is represented by alpha. Therefore, it is defined as the ratio of output current, that is IC, to the input current, that is IE. Therefore, beta is IC by IB, alpha is IC by IE. Similarly, common collector configuration also considered, in which case the common point is collector. Collector is made common for both input and output. Emitter is the output, base is the input. IE by IB is equal to gamma, where gamma is the common collector gain. That is output current IE divided by IB, because collector current is made common. Now we will discuss only beta and alpha. Now there is a definite relations between alpha and beta. If you know alpha, that is the current gain in common base, you can calculate the current gain in the common emitter mode. Or if you know beta, that is the gain in the common emitter mode, you can calculate the gain in the common base, that is alpha. If beta is known, alpha can be calculated. If alpha is known, beta can also be calculated. And if alpha, beta are known and any one current known, the other current can be calculated. Now let us obtain the relations between alpha and beta. So the relation between alpha and beta. So we know that the emitter current is divided into two parts, one base current and another collector current. but base current is only 5% of the emitter current, and the 95% of the emitter current will go to collector. Therefore, the emitter current IE is equal to sum of the base current plus collector current, in which IB is very small. Therefore, IE is almost equal to IC. That is, whatever the electrons present in the emitter that carries emitter current almost equal to almost all electron goes to collector. The collector will collect almost all electrons, where the base collects only few electrons. Since IB is very small, in general we can write IE is equal to IC. But however, the emitter current is equal to sum of the two currents, base current plus collector current. Now dividing throughout by IB. So you get IE divided by IB is equal to IB by IB is 1 plus IC by IB. Now this can be solved like this. I will write this as IE by IC into IC by IB. The value will never change. Instead of IE by IB, I will write IE by IC into IC by IB. IC get cancelled, IE by IB. Therefore, this can be written like this, which is equal to 1 plus IC divided by IB. And I will again write this like this, IE, IC by IB. I will retain as it is, IC by IB divided by IE by IC. When go to the denominator, it becomes IE by IE by IC. When it goes to denominator, it becomes IE IC divided by IE, which is equal to 1 plus IC divided by IB. Now, what is IC by IE? You see here, IC by IE is equal to alpha, current gain in common base. What is IC by IB? IC by IB is beta, current gain in common emitter. Therefore, we can write this as IC by IB is beta divided by IC by IE is alpha, which is equal to 1 plus IC by IB is beta. Now cross multiplications. You get beta is equal to alpha into 1 is alpha plus alpha into beta. Take this alpha beta to the left side. You get beta minus beta alpha is equal to alpha. When it comes to the left side, it is beta. Beta is common. Then 1 minus alpha. When you take this alpha beta to the left side, it becomes minus alpha beta. Beta minus beta alpha equals alpha. Beta is common. Then 1 minus alpha is equal to alpha. Or beta, that is the current gain in common emitter mode, is equal to alpha divided by 1 minus alpha. This is very much greater than 1 because this denominator is 1 minus alpha, which is very much less than alpha. Therefore, ratio is very much greater than 1. That is, the current gain beta in common emitter configuration is always greater than 1. Now, consider the same expression, that is this expression. Beta is equal to alpha plus alpha beta. Beta is equal to alpha plus alpha beta. From this, you can take a common factor alpha. This is beta is equal to, if you take alpha as common, 1 plus beta, or alpha is equal to beta divided by 1 plus beta. So this is the relations between alpha and beta. This is also relations between beta and alpha. Here you can calculate beta if you know alpha. Here you can calculate alpha if you know beta. Since 1 plus beta is more than beta, the ratio is always less than 1. So current gain in common base, that is alpha, is less than 1. Current gain in common emitter, that is beta, is always greater than 1. So this is the relations between alpha and beta. If you know the current gain in one configuration, you can calculate the current gain in the other configuration.